Okay, this is a pre-calc review going over some fundamental algebra concepts. We begin with graphing, and these graphs are all just linear equations. There are three forms of a linear equation graph: structure, linear function. One of them is called slope-intercept. You guys often think about that more likely as y equals mx plus b. What's the b? The y-intercept, good. And what's the m? Slope, good. Thus, it's called slope-intercept. Slope-intercept. Second form is called standard, which is of the structure ax plus by is equal to c. In this structure, you cannot see the slope. You cannot see the y-intercept. So this probably is the least valuable one for graphing. But one of the great ways that this comes up at times would be if you have something like 6x minus 9y equals 36. You could graph it with x and y intercepts. If you could create 2 points, you can connect those points and make a line. What do we know about the x-intercept? Every x-intercept has one thing in common. Good, the y value is 0. So if I consider that this y value is 0, negative 9 times 0 is going to be 0. So if 6x is 36, what's x? 6. There's our x-intercept. And I could find the y-intercept the same way. Every single y-intercept has the same x value, and that x value is 0. So if I plug in a 0 for x here, 6 times 0 is 0, so that goes away. Negative 9y equals 36. So what's the y value of the y-intercept? Negative 4. And then with those two pieces of information, 2, 3, 4, 5, 6, 1, 2, 3, 4, you'd be able to graph that function. Oftentimes you can create a transition. In other words, change the standard form into slope-intercept to get that view as well. Could I ask somebody in the end to turn off the lights? That might make the screen a little bit brighter. Thank you. The third form is called point slope. Great. And that's of the form y minus y1 equals m times x minus x1, where y1 and x1 are components of a single point that you know exists on the graph. So for example, y minus 2 equals 3 times x plus 2. You'd say, all right, well, I see that the slope is 3, and I've got a coordinate, negative 2, comma, positive 2. It's the opposite of the signs. And then with that single coordinate, negative 2, positive 2, I'd be able to apply the slope. 1, 2, 3 over 1, 1, 2, 3 over 1, and graph the equation. Any questions on graphing linear equations? Okay. Going back to what? This part? Y minus y1 equals m times x minus x1. Yep. Okay, so that pretty much takes care of the first page. Page 2, still slope-intercept, slope-intercept. Well, let's do this. Let's take a look at number 9. If I were going to write the slope-intercept form of the equation here, what information do I need to be able to write an equation? Slope and intercept, right? Like ideally, if I were able to give you the slope is equal to and the y-intercept is equal to like 0, 3, slope of 2/3, then you'd say, oh, this is super easy. It's just y equals 2/3 x plus 3. But most times you won't be given that information. You won't be given both the y-intercept and the slope. If you're given 2 points like this, you can find the slope. How do we find slope? Remember the equation? y2 minus y1 over x2 minus x1. You might remember it as rise over run. So in this case, I'll take my y values. This is y1, y2, and I'll take y2 minus y1. So 0 minus 4. And then I'll take x2. I got to make sure to keep them in the same order. x2 minus x1, negative 4 minus negative 4. So that gives me negative 4 over 0. What does that mean? Negative 4 over 0 is what? Undefined. That does not work. So if we think about a slope going slightly up like this is a low positive number. A slope that's flat is 0. A slope coming downhill would be a negative number. So what does this mean when the rise is some value, but the run is going nowhere? It's a vertical line. So let's look again. The equation we're looking for is some equation that ties these 2 points together. In other words, it could be something like negative x, if I'm just looking at this one. Y equals negative x would take this negative 4 for x and turn it into 4. But does that also work for this one? It doesn't. More simply, what's true about both of these? They both have an x value of negative 4. So in other words, almost. The rule is that every single point on this line shares an x value of negative 4. We don't care anything about the y. This one is x equals negative 4. That's the equation, not a traditional y equals mx plus b. Let's try a different one that's a little bit more interesting. How about number 14 here? What's our slope? y2 minus y1, 2 minus 4. x2 minus x1, 4 minus 0. Negative 2 over 4 reduces to negative 1/2. Now what? I've got a slope. That's helpful. You have a couple of choices. My slope is negative 1/2, and I've got a coordinate of 0, 4. What point is that? The y-intercept. So I have slope intercept. So I can just plug this in like that. Oh, but this doesn't ask for slope intercept form. It asks for standard form. Thank you. How do I change this slope intercept into standard form? What's wrong with this? Is the y in the right place? It is. Remember, standard form is where we have ax plus by equals c. This is a constant. We got the y's on the left and the x's on the left. Do we have our y's on the left? Yeah, so the y's okay. It's this x that's wrong. How do I move this to the other side? So now I've got 1/2 x plus y equals 4. Is that standard form? Trick question. In standard form, we expect a, b, and c, the coefficients of each of these, to be whole numbers. We don't leave them as fractions. So how could I change this so that instead of this being a fraction, it's a whole number? Multiply everything through by 2. Busting that fraction. So if I do 2 times everything, I get 2 over 2x plus 2y equals 8. 2 over 2 is really 1x plus 2y equals 8. Any questions on that? What's your confidence doing this kind of thing? 5, I got this. 3, I'm a little rusty, but I think I did this well. I'll do it again. 1. I don't think I ever learned this. Okay. I see 1s through 4s. Okay. Next chunk is factoring. Come on over. Let me give you a sheet here. Thank you. What's your name? Dennis. Okay, thanks. What does factoring mean? It's weird because it's undivide. Excuse me, unmultiply. But is it divide? It's not. So what factoring means is I'm going to take each component and break it out. For example, 5 times p minus 3 times 5 times p. What do I have common to each of these terms? Terms are things separated by plus or minus. What's common? 5 and p. So whatever it is that's common, I pull that out front. What remains is what's on the inside. This is called the greatest common factor. And it's the first step every time you factor. Once you've done that, depending upon what you're left with, you'll employ other factoring methods. What's the process for factoring something like this? A quadratic trinomial. You guys use diamond box? Start with a diamond and say, these two multiply together to make 24v squared. This middle term is negative 11v. I'm looking for two numbers that multiply together to make 24v squared, and yet add together to make negative 11v. What are those numbers? Let's see, 24 could be 24 and 1, 12 and 2, 8 and 3, 6 and 4. And then when I go down one more, I'm at 4 and 6, which is the other side to it. Thank you. Hold on. Which of these is going to give me an 11? 8 and 3. Oh, but I need a negative 11. Good. Negative 8v, negative 3v. Those multiply to make a positive 24v squared. Add to make a negative 11v. That's what I need. Now, I'm going to present this as a factor by grouping. I know that a bunch of you would simply go to, okay, that means it's v minus 8 and v minus 3 and say I'm done. And yes, that shortcut will work for this particular problem, but I'm going to take you through the full process that works for every style problem. This original problem, where to go? Here, can now be rewritten as v squared minus 8v minus 3v plus 24. Do you agree these equations are the same value exactly? By breaking out the negative 11v into negative 8 and negative 3 that I strategically found down here, I'm ready to factor by grouping. And I'm going to do this same greatest common factor. What's common to these two terms? V. So I'll pull that out. And when I pull a v out of this, what am I left with? When I pull a v out of this, what am I left with? Now I'm going to do the same thing here. What's common here? 3, and I'm going to actually pull it out as a negative 3. In other words, I'm really going to treat this as plus negative 3v minus negative 24, because I want this to be nice and clean. When I do this, I'm going to pull out, okay, there's a negative 3 in each of these because this is really negative 3 times 8. So I'm going to say minus 3 times v minus 8. Pro tip, if I've done this correctly, what's true about these inner parts? They're the same. They have to both be v minus 8. If you get this one as v plus 8, you made a mistake in what you pulled out. It's not quite there. Now, remember when we did this p thing here, and we said, what's common? And we pulled out whatever was common. Consider this a term, v times v minus 8. And negative 3 times V minus 8. What's common to both of those terms? Isn't the V minus 8 common? So I'm going to pull that out front. And when I pull that away, what's left here? And what's left here? So you get V minus 8 and V minus 3. This works beautifully when you're doing like a lead coefficient that makes it harder for you. And especially we're going to get to numbers 26 and 27 ask you to factor by grouping. These are actually cubic functions, but you can factor them that exact same way. Look for what's common in both of them, what's common in both of these. Factor by grouping. We also have one special case that's of paramount importance. You guys did this well yesterday. What does the difference of squares say? If I have x squared minus 100, how can you factor that? Is x squared a perfect square? It is. What's the square root of x squared? X. That means this first term is going to be x and x. Is 100 a perfect square? It is. What's the square root of 100? 10. So I'm going to put 10 and 10. And this is the difference of squares. Subtraction, difference. Therefore, I'm going to have 1 plus and 1 minus. We will use difference of squares a ridiculous amount in this class. Get comfortable with this. Use this whenever you can. In fact, can we use difference of squares to factor this? Is x squared a perfect square? Is it a difference? Is there a square root of 5? Yeah, it's square root of 5. So couldn't I write this as x plus root 5, x minus root 5? Sometimes that's really helpful. One more. What if I have x squared plus 9? Is that a difference of squares? It's not, but could I write it as a difference of squares? Could I make it x squared minus negative 9? Now, using the idea of difference of squares, what could I write? X plus minus, what goes here? Say again?
3i.
Square root of negative 9, right? Well, this is the same as the square root of 1, negative 1, times square root of 9. What's the square root of 9? 3. What's the square root of negative 1? Do you remember this? I. Good. So in other words, this would be x plus 3i, x minus 3i. What I'm doing right here, please don't let this melt your brain. I'm like giving you a preview of how we're going to get into this stuff later. This is not like next week. This is like in a month and a half. Okay, so don't let this scare you. All right, so you'll be factoring sum and difference of cubes. Do you remember that from advanced algebra? 5, yes, that was my buddy. 3, we did it. I'd have to look it up. 1, I know we didn't do it. Good, so you can look it up. I don't expect you to have that memorized, but you should refresh yourself with it, right? How is it different when we say solve by factoring rather than just factor? The letter? You solve for x or r or whatever, right? There's an equal sign. So what I'm going to do is bring this all to one side. Let's say this one. I'm going to move it all over here. N squared plus n minus 42 equals 0. I look at what kind of problem this is. This is a quadratic trinomial, so I can do that diamond problem. I've done this enough times now that I'm pretty fast with this. I know this is going to be n plus 7, n minus 6. And now I'm going to apply the zero product property. What does that say? If I got this thing times this thing equaling 0, one of them has to be 0. Equal n plus 7 equals 0, so n is negative 7. Or n minus 6 equals 0, so n is equal to positive 6. That's how I'll find both my answers. We did a little bit of that last class, right? What does FOIL mean? First, outer, inner, last. It's the distributive property, but it's when you use a polynomial, multiple terms, times another polynomial. So what that tells us is, for example, we're going to take this 2x here, and we're going to distribute it across each term in sequence. And then we'll come back and take the second part, y, times each term. I'm going to do this one here because I think this is worth a little bit of focus. Okay, so first I'll do the 2x, the first terms. 2x times 7x squared. The constants multiply together, giving me 14. Now the x's multiply together. X to the first times x to the second is x to the third. Now I'm going to keep going with this 2x. I'll do the 2x times negative 6xy. That's negative 12 x squared y. Then I'll do the 2x times the last term, plus 14 xy squared. Now I move on to my second term in my first polynomial. I'm going to multiply y times each of these. So I'm going to get plus 7 x squared y minus 6 xy squared plus 7y cubed. And now I'm going to combine like terms. This is my only x cubed term. I have two different x squared y terms. Negative 12 and positive 7 is a negative 5 x squared y. I have two xy squared terms. Positive 14 and a negative 6 is a positive 8 xy squared. And then I have this lone plus 7y cubed. And that is the result of quote unquote foiling. It's not really called foiling. It's the distributive property with polynomials, multiplying polynomials. How's that feel? 5, that's doable. 3, that's tough, but I can get there. 1, that's like magic. I don't believe in magic. Okay, good. Next piece is simplifying radicals. Well, let's do 40 first. What we're asking ourselves is if we were to take all this stuff and factor it out, 2 times 2 times 3 makes 12. I've got two x's and I've got a y. Some of you had me for geometry. Do you remember my somewhat inappropriate discussion about square roots? Back in the 70s, they used to have these things called single bars. And a single bar was like a bar, but it had a sign out front that said, this is for singles. So in this case, what you're doing is when you go into that bar, you're looking for someone who's exactly like you. So the 2 and the 2 find each other. They found love. Do they need to stay in the singles bar now that they've found their partner in crime? No, they can leave. And when they leave, they're one of those like ridiculously sweet couples that comes out arm in arm and looks like they're a single person. They come out like a single two. Who else gets to meet up and leave? The two X's come out as a single X. And who's stuck inside looking for love? Three? Why? I don't know. They're really nice. Okay, so 2x root 3y would be the way this simplifies. The reason I like this analogy is that what if the sign out front has a 3 on it? What kind of singles bar is that? It's looking for thruples. So I'm going to take this root 81 and I'm going to make 81 3 times 3, which is 9 times 3 times 3, x, x, x. I'm going to go y squared, y squared, y squared, y squared. So since this sign out front says, hey, only come in here if you're looking for a thruple, what do I pull out with this 3's? These 3 make 1 3. What do I pull out of the x's? A single x. Out of the y's, I'm going to pull out a y squared. Who's left inside looking for love? 3y squared. And that's a cube root up there. Can I combine these two terms? Negative 2 root 12 and negative root 3? I can't. Root 3 is like 1 root 3. It's like 1x. I can only combine it with another x. These two are different radicands, things on the inside here. But I can simplify this first, just like we did up here. Root 12 is the same as root 2 times 2 times 3. So who pairs up? The 2, leaving a root 3 in there looking for love. So in other words, I can now treat this as 3 times 2 root 3 minus 2 times 2 root 3 minus root 3. When you multiply, things on the outside multiply together. And if you have things on the inside multiplying together, then they do too. But this gives us 6 root 3 minus 4 root 3 minus root 3. If you've got 6 pineapples and you subtract 4 of those same things, 4 pineapples, what do you got left? 2 of them. So in this case, you'd have 2 root 3 minus root 3. And if you have 2 of something and you subtract 1 of them, what do you have left? Just 1 of them. All right. Last page. If I were to give you a fraction like 3/6, does that feel like it's simplified and ready to go and you're all good with it? Or does that just like make you twitch a little bit? You're like, hey, that's improper. You can't do that. You'd want to change that to what? 1/2, right? In the same way, you should feel that way when you see a square root in the denominator. You'll never leave a square root in the denominator. So what can I do to make this square root go away? Yeah. Excellent. It's called rationalizing. And I know you might be tempted to square it, but if you had 1/2 and you squared it, does it still equal 1/2? Or does it change value? It changes. So you can't multiply this thing times itself or square it to get rid of that square root. Instead, you rationalize it by multiplying by root 18 over root 18, the denominator. Because these are both under the little house, you'd say that this is 10 times 18 under the house, and this is 18 times 18 under the house. Well, wait a minute. If these two match up, what happens to this denominator? Who pairs up? The 18 pairs up. It comes out as a single 18. We got rid of the radical. That's what we wanted. And we should try to figure out how to rationalize this as well. I'd multiply this as 5 times 2, change 10 into 5 times 2, and change 18 into 2 times 3 times 3. Who gets to pair up inside this radical? There's a 2. There's a 3. They're multiplied. This root 5 is still stuck inside looking for love. And there's an 18. 2 times 3 is 6 over 18. That goes in 3 times. So this would settle on root 5 over 3. Five, this is kind of fast, but it's really helping me. 3, it's more fast than helpful. 1, I lost track hours ago. Okay, good. Yeah. Yeah. What about 47 here? What's screaming at you to simplify here? I know your 3 over 6 looks like 1/2. You're not going to leave it as 3 over 6. And I said you got to remember to keep all square roots out of the denominators. What's wrong with 47? What's I? Isn't that a square root? So you got to get rid of it. How do I get rid of the I? Can I just multiply by I over I? Is that going to work? I mean, that's what we did here, right? We chose whatever was offending us on the bottom, and we multiplied by that over itself. If I do I here over I, I'd get 9I on top, but this I would distribute, giving me still an I here. It would clean up here. So to clean this up, I have to do something called the conjugate pair. If this is -4 minus 8I, I'm going to multiply it by -4 plus AI. And I'm going to do it over itself, so it's a version of 1. This will be distributed, so I'm going to get -36 plus 72I on top. And what happens on the bottom? This is also distributed, FOILed. I get -4 times -4 is 16. -8 times -4 is positive 32I. -4 times positive 8I is negative 32I. -8I times positive 8I is negative 64I squared. What happens here in the middle? They cancel. Why? Because these are like the difference of squares, right? X minus 3, X plus 3. -4 minus 8I, -4 plus 8I. When you multiply those, the middle term drops out. What happens with I squared? Good. Turns into -1. So this really becomes 16 plus 64, which is 80. So now I've got -36 plus 72I over 80. I'm looking for big numbers that can divide out of both of these. 9s can come out of that. 6s come out of that. Let's go with a 4. So -9 plus, what is that? 18I with a 4 out front over 4 times 20. So this is my final answer, -9 plus 18I over 20. Last piece is some work on fractions. How do you multiply fractions? Top, top, bottom, bottom, right? So I would just multiply these times these, and these times these, and see if anything cancels. In this case, I'd treat it as one big fraction. What should I do with this one? Factor it. I know that this is going to become r minus 9, r plus, nope, that's not right, 7 and 2. R minus 7, r plus 2, and it's being multiplied by r plus 3, and that's over this chunk, which is r plus 3 times r minus 10. Once I consider them as multiplied together, it's like one big fraction. So whatever's on top and the bottom cancels out, and I'm left with what's on top. So that would be r squared minus 5r minus 14 over r minus 10. Can I cancel this r squared with this r down here? I cannot, because canceling means dividing. It has to be a factored out piece to cancel out. It can't just be added or subtracted. So when you multiply fractions, you go top times top, bottom times bottom, and simplify. What about when you divide by fractions? Multiply by the reciprocal. Keep, change, flip, right? I'm going to keep this fraction alone, 4 over x minus 7, change the sign from division to multiplication, and flip this to be the reciprocal. And then I'll factor and cancel out parts as I can. What about 53? Good. It's the same as this. It says fraction divided by fraction. It's just written a different way. So I'll change it to this fraction times the reciprocal. Okay, I've done most of your work for you, but I think that gives you a good nudge. Please finish up the even numbers as your homework. If you find that you're doing a problem and you don't understand it well, I strongly urge you to consider doing the odd number next to it as well. The answers in the back are for all the odd numbers.